With ligand substitution, when you change a ligand, particularly with chloride because they're larger, you're going to get a change in coordination number. And that means there are, instead of 6 lone pairs of electrons, you're swapping it for chloride, which are larger, and so you have a coordination number of 4. This will change the colour of the complex. If you now change the polydentate ligand, for example, here we've got a hexa aqua iron 3 ion, and we use a polydentate ligand such as Edta. The reason why the Edta complex is more stable is not because it grips greater, because it's still a coordination number of 6. It forms 6 coordinate bonds. The reason why it's more stable is because what happens is if you look on the left-hand side, you have a charge, you have 2 species, and if you look on the right-hand side, you have 7 species. So there is a greater entropy, there is an increase in entropy, which is why the reaction proceeds to the right, and it's much more feasible. There is a charge mistake. Could you spot the charge on the complex? What should the charge be on the complex? So whenever you swap for a monodentate ligand, for a polydentate ligand, you're always going to get an increase in entropy, and this is called the chelate effect. See missing off effect there, I've spelt it the French way. So the reaction will always proceed forward, so the Edta complex is more stable. So let's now look at another example where we have a bidentate ligand. Bidentate ligands have a coordination number of 2. They can donate 2 lone pairs of electrons. So their complex will still be stable than those made up of a monodentate ligand, but less stable than a polydentate ligand. The bidentate ligands you need to know are diaminoethane, which is ethane with 2 amino groups on, and there you can see the 2 lone pairs of electrons. So diaminoethane, or N, can donate 2 lone pairs, and the other one is the ethane dioate ion. Any dioic acid, butane dioic acid, propane dioic acid, can act as a bidentate ligand. And the reason why they're more stable, you can see here, is on the left you have 4 species, and on the right you have 7 species. When you write the equation, don't forget to balance it. 3 bidentate ligands will replace 6 monodentate ligands. So make sure you balance the equation and don't forget to put 3 of the bidentate ligands, substituting the 6 water molecules. Again, you can see the chelate effect, 7 particles on the right-hand side and 4 particles on the left. The right wins, there's been an increase in entropy and increase in disorder. Now, all ligand substitution reactions have a change in colour. There is no precipitate. So it's a change in colour because, remember, when you change the ligand or the coordination number, you affect the splitting of the D subshell. So these will in effect change the colour of the solution. Unless the ligand, the overall complex has no charge, then it will not precipitate. So remember why you get coloured solutions and why there's going to be a change in colour. The ligand splits the D subshell, and then as light hits the D subshell, an electron will become excited to the higher D subshell, and visible light will be absorbed. Remember, when visible light is absorbed, to make that electron transition, the frequency of the light, which is equal to, so the energy The difference in energy is equal to Planck's constant H times the frequency of the visible light that's being absorbed. Any light that is not absorbed is reflected, and that is the colour that you perceive the solution to be. So it's excited d electron. Let's now look at acid-base reactions as opposed to ligand substitution. So in this case, the transition, the hydrated metal ion, will behave as an acid. And you will see precipitation if, when the acid reacts with a base and protons are lost, if the overall complex loses its charge, it will then lose a +2 charge, and the 2 hydroxide ions will remove 2 protons. It's not a ligand substitution. You are not breaking the coordinate bonds. It's behaving as an acid because the transition metal complex, the hexa aqua ion, is simply donating 2 protons. So the 2 hydroxides there, as you can see, the 2 hydroxides here have removed 2 protons from here to form water. The precipitate, therefore, has this formula. It's gelatinous because of the presence of water, no charge, and therefore it precipitates. And that is an acid-base reaction. Now, metal 3 carbonates cannot exist, and that is because 3+ ions, because of the acidic nature of this hexa aqua ion, if carbonate ions are present, these will behave as a base. They will rip off protons. When you come to balance this equation, 3 carbonates will react with 2 hexa aqua ions. If you look at the charges, 2 times +3 is +6. The carbonate rips off protons from this species, from the hexa aqua. When it rips off protons, it will fizz because carbon dioxide is produced and water. So make sure you can balance this equation. You will see a precipitate, which is the hydroxide, not the carbonate. It is not the carbonate. Not the carbonate. Carbonates, 3+ ions, do not exist. Only 2+ ions. So our 3+ ion is much more acidic than our 2+ ion because the 3+ ions, remember, have a greater charge density. So they polarize those tiny water molecules, pulling electrons towards themselves, and the little hydrogens are held really weakly. They're almost naked protons, ready to be released. 2+ ions are not as acidic, which is why they can form carbonates. 3+ ions do not form carbonates. Remember, 3+ ions do not form carbonates.